Now, and look, this is a really good regression model. But if we add additional independent variables, in other words, if we try to find other predictor variables that might help explain our sales beyond just how many sales calls a person makes, that's why we would go from a one variable simple regression model to a multi-independent variable multi-regression model. So now let's go back to our data. And what I'll do here is I'm going to bring in 3 more independent variables: experience, distance, and system. Now, before I actually run the multiple regression, I want to make a comment about system, because as some of you look at the example in the book, you could find this confusing and contradictory to what I've said. If you notice here for variable x4, where I've got highlighted, that's a yes-no variable. And it has to do with whether they use some type of a new high-technology sales monitoring system. Well, you know by this point in the class that any variable that is set up as a yes-no variable, that's actually a 2-level nominal variable. Yet, I've told you that in multiple, well actually simple regression and multiple regression, that we should only use quantitatively scaled variables. That is, variables that are scaled interval or ratio. So it's not that Oris doesn't know what he's doing. It's not that Oris is trying to trick us. But while I want you at this stage of your development to only be doing simple regression and multiple regression with variables that are interval and ratio and scale, actually after the Thanksgiving break, I will show you how to use regression analysis with nominal data. It just so happens Oris introduces this to his students earlier in the semester than the way I choose to organize the class. So nevertheless, since Oris has it in his model, and I want our results to be consistent with what's in the book, you see here that we have a 2-level nominal variable that we're using. And if you notice, this is all zeros and ones. And you may notice in the book, Oris uses the term dummy variable, D-U-M-M-Y. And that's just when a variable is set up as a 0 or 1 scale. Okay? So now we're going to run a multiple regression with 1 dependent variable and 4 independent variables. And we'll do this much like everything else in the past. We first click on add-ins. We then go to Megastat and click on Megastat. We drag down to correlation/regression. We drag across and down to regression analysis. So this is all the same as we did with simple regression, except this time you'll see the screen looks differently in some ways than what we have for simple regression. Let me first clear this out. Okay. So it asks for the independent variables, and notice here it's got, S in parentheses, because if we use this screen to do simple regression, we would only have 1 independent variable. So our 4 independent variables are calls, experience, distance, and system. We highlight the column headers and all of the data. And then for our dependent variable, that's the same as when we had our as when we had our simple regression model. So it's that column, including the column headers sales. Okay. Now, I misspoke a few minutes ago. Let me make sure I'm clear about something. While this dialog box is exactly the same as we use for multiple regression versus simple regression, in simple regression, we don't use any of these items down here. But in multiple regression, as we go on over the next couple of weeks, you'll learn how to work with some of these items down here. For this particular example, I'm not going to use this, but typically in multiple regression, we use at least several of these items down in this portion of the screen. So just to make that clarification. But I've highlighted my area for my independent variable. That's calls, experience, distance, and system. And I've highlighted my area for my dependent variable. That's the column sales. So I'm going to use 4 independent variables to try to predict the value of my dependent variable. And remember, if you will, when we only used sales calls to predict dollar sales, our explained variance was about 80%, if I recall correctly. So now let's see whether adding 3 more variables material improves the ability of our regression model to predict our dependent variable dollar sales. So I click on OK. Now this is very typical output that you get not only in SPSS but any other stats program for that matter that runs multiple regression. The first thing I want to do is direct your eye to these 3 items here: R, adjusted R squared, and R squared. Recall, if you will, that I said that I want you to pay attention to the adjusted R squared. If we go back and look at the simple regression analysis, the R squared with simple regression was about 80%. So adding 3 new variables has in total moved our R squared value, or explained variance, from about 80% to about 86 to 87%. So we increased 7 percentage points. Okay. Now recall also that the model help predict the dependent variable, and to assess that we look at the p-value in the ANOVA table, and that's a really small p-value. So we reject the null hypothesis. We conclude that adjusted R squared is greater than 0, comes as no surprise to us. So we've concluded that yes, the regression model does help predict our dependent variable, and we can see here evidence that adding in more variables improved the predictability of the model from about 80% to about 86, 87% of explained variance. But then the question becomes, are all of the independent variables helpful in predicting our dependent variable, or might some of our independent variables be ineffective in that regards? To address that question, we have to look at this column of p-values. Remember, this p-value down here tells us, does the regression model help predict the dependent variable? Let me rephrase that. Does the regression model in the aggregate help predict the dependent variable? We've rejected that null hypothesis. We've concluded that yes, the regression model does help. Now we go up and look at these p-values to try to figure out, well, which of the independent variables is effective and which of the independent variables is ineffective in helping predict our dependent variable of interest, dollar sales. You'll notice here that the p-value for sales calls is very small. 8.03 e to the minus 7 is a very small p-value. So we would reject the null hypothesis for sales calls, and we would conclude that the slope of the regression line for sales calls is greater than 0. Recall in our earlier single regression model or simple regression model, the slope of the line for calls was, I think, it was right around $2,000 if I remember. So the slope of this line remained relatively unchanged. Notice here the p-value for years of sales experience is greater than 0.05, so we fail to reject the null hypothesis for that. Now at this point, we don't know whether experience is just not effective in helping predict dollar sales. There may be a multicollinearity issue that causes us to get a large p-value here. I'm not going to explain multicollinearity at this point, but I only mention the word so that when you read it in the memo and when you see how we handle it in a subsequent mini lecture, that you'll begin to develop some familiarity. And then we see here our other 2 independent variables, distance and whether they use the high technology system. The p-value for both of those independent variables is less than 0.05, so we reject the null hypothesis for each of them as well. Thus, at this point, we conclude, number 1, the regression model helps predict the dependent variable, and number 2, 3 of the 4 independent variables is effective, at helping predict the three of the four independent variables, is effective at helping predict the dependent variable. The only variable that we have thus far suggesting that it does not help predict the dependent variable is for our independent variable experience. Okay? Now, I'm not going to go through these upper and lower bounds at this point. I think you've probably gotten to the point where you understand 95% confidence intervals and upper and lower bounds well enough. But I will expect you to be able to interpret what the upper and lower bounds mean. If you have questions in that regard, feel free to ask me. Hopefully this gives you a good foundation in not only how to run Megastat, but how to begin to interpret the output and how your eye should travel. Okay, again, let me just real quickly. When I look at multiple regression output, the first thing I do is my eye goes here to the adjusted R-squared. Next, my eye goes down here to the p-value for the ANOVA table, which should confirm what I intuitively would have interpreted with the adjusted R. So my eye first goes here, then my eye goes down here, and then my eye goes to each of these. And I'm doing that to try to figure out, does the regression model help predict the dependent variable? And once I conclude that it does, then I'm interested in which of my independent variables is effective, which of my independent variables appears to be ineffective. And then the next thing I do is I would write out my regression model using each of these coefficients to show how much change in my dependent variable sales do I expect based on changes in each of my independent variables. Okay. Hope that helps. And in our next mini lecture, we'll continue to build on this, but we will add some diagnostics to it. It's not that we'll learn any more about the regression model itself. We'll just be able to learn some things that will give us better insight as to the overall quality of our multiple regression model. Thanks.